Okay, so we had a lively conversation about approaching the speed of light today, which a few people tried to derail, but it went pretty well. Anyway, there are a few things we missed today, and they're all fairly straightforward, but I want to make sure you get them. So your homework this weekend, the price of interest is, you're going to take a little bit of notes first, and then you'll do W59. But it's not too bad. So here's what it is. We left off drawing the gravitational field. Now, what the gravitational field does is it allows the gravitational force to be transmitted between objects. So the connection here is that whenever there is a gravitational field, then objects within that field will feel the gravitational force. So here's some simple examples of experiencing the gravitational force, which present company may want to write as we do, and then you're done. All right, so this says draw the FG vectors and label their magnitudes on the diagrams. So, be quiet over there. Diagram number 1, a bison. Does the bison experience the gravitational force? Sure it does. It's sitting on Earth. Earth is down here. So you find the bison's approximate center. There it is. And where is it being pulled? This is not now the gravitational field vector, but what's the actual force on it? It is being pulled down toward Earth's center. We put a downward arrow, and we call that Fg for the force of gravity. Now, we have a specific way to calculate this. We're going to use Shawty because we are on or near Earth. However, we can approximate right now. I had you talk about your own mass and your own weight, and we approximately turned kilograms to newtons on Earth by multiplying by 10. So this is approximately 700 times 10, which is 7,000 newtons. You can also write that as 7 kilonewtons, even 7 times 10 to the third newtons. All right, cool. There it is. What you have just drawn a piece of, this is an incomplete version, but what you have just drawn a piece of is what we call an FBD. FBD stands for free body diagram. And a free body diagram is just a force diagram, which is what it sounds like. You draw forces on the object. Now, I said this is an incomplete FBD, free body diagram, because I've only drawn the force due to gravity. There are other forces on these objects, but that's the only one we're going to worry about for right now. The next object is a baseball. A baseball at the peak of its flight. Maybe this is a throw-up problem. It got hit, it got tossed, the ball's going straight up. At the very peak, it stops moving. But does it stop being pulled by gravity? No, it's still pulled down toward the Earth. So there is an Fg right here. How much is that Fg? Well, we have 145 grams. First, we should convert that to kilograms. I like to multiply by fraction, gram on the bottom, kilogram on top. And if you look at your reference table, 1 kilo is 10 to the third, or 1,000 grams. Convert, and you end up with 0.145 kilograms. And then if we were to approximate that in newtons, on Earth you can multiply by 10 and you approximately get 1.45 newtons. All right, good. Next one, Felix Baumgartner. Though he did not weigh 220 pounds, with his suit he approximated that. He too is being pulled by the Earth, directly downward, Fg. Now, how can we figure out what the Fg is on Mr. Baumgartner? Well, if you recall, it's 2.2 pounds per kilogram. So his 220 with suit is convenient because 220 pounds is 100 kilograms. And then 100 kilograms is approximately 1,000 newtons, or 1 kilonewton. We also have a box on a ramp. Now, the fact that it's on a ramp is largely irrelevant to the fact that it is being pulled gravitationally by the Earth. The Earth is a big object. Directly down below is its center. Here is your Fg, straight down. Now, I don't need to approximate this one. It is described as a 20 Newton box. That means that its weight is exactly 20 newtons. And that exactly is not a sig fig comment. Finally, moon in orbit. Here's the Earth. Here's the moon. These darker colors so you can see it against the gray. Here's the moon. Does the moon experience a gravitational force? Yes, it does. As always, it is toward the center. Let us not get fooled into thinking every arrow is down. Toward the center is this way, toward Earth's center. FG, and we actually figured this out a few pages ago in the notes. We already calculated this. The answer was roughly 2 times 10 to the 20th Newton. There is your first round of free body diagrams. Put away, you got work to do. Man.
I've been out the whole time.
Man.
You saw.
Okay, let's go on the next page. Next page, we just have a couple applications of, wait, who? What? Who's that there? Hey, yo, Shawty! Come on, Shawty. Look at Shawty. Look at Shawty looking all cute. Come on over here, handle this problem for us. Oh, Big Ugly gonna be mad. All right, so let's go look at the questions here. There are 3 questions that are very easy to set up. What do we need? Please don't break stride. It's like some of you on the mega assessment. Just set up the givens. Givens with units. Here we go. Determine the force due to gravity. Straight away, they're asking for the force due to gravity. Read no further. Come over, Fg equals question mark newtons. The force due to gravity. Acting on a 50 kilogram mass. Okay, they told us the mass. M is 50 kilograms. On the surface of Jupiter, where the gravitational field strength, we looked that up yesterday, but in your reference table on page 6, that's little g, gravitational field strength is 26 newtons per kilogram. Now, I will tell you straight away, it is worth your while to recognize when you are on Earth and when you are not on Earth. Because when you are on Earth, the Fg, the weight, and the little g, the gravitational field strength, are one thing. And when you are not on Earth, they change. So it's actually a nice idea. You would get this question anyway. But it's a nice idea to recognize that the gravitational field strength on Jupiter, little j, is 26 newtons per kilogram. What is the force due to gravity while it's on Jupiter? And they gave you the mass while it's on Jupiter. Not bad to subscript that just to keep yourself sharp. Equation. Listen, Big Ugly can handle this for you. But you don't need Big Ugly on this. Let's just keep it our own little secret. We're going to leave Big Ugly on the side. We're just going to call it Shawty for this one. So here we go. Equation. G equals Fg over M. We're trying to solve for Fg. Do a quick rearrange. Fg equals Mg. And at this point, substitute and solve is about as easy as it gets. Fg equals 50 kilograms times 26 newtons per kilogram. You will get 1,300. For those of you who might take physics again in the future, we have defined within physics, you won't really know why on the basis of my comment now, but anytime you have an attractive force, it actually comes out negative. Don't worry about that in this class. I will never test you on that in this class, nor will the regents, at least not within gravity. But yes, attractive forces in physics turn out to give you negative answers. Again, the only reason I mention that is because perhaps when you see this in your future courses in actual college, that may come into play and you say, oh yeah, I remember that. Maybe. All right, next one. Get them givens with units. What is the magnitude of the gravitational force, again, Fg, acting on a 2 times 10 to the third, a 2,000 kilogram meteorite that is freely falling towards the surface of planet X with an acceleration, A, of 11.2 meters per second squared. Now, You could probably answer this problem without issue. But let me point out the comment we made at the bottom of the other page. It's also written up here in print. If it is free falling at 11.2 meters per second squared, well, that means that the gravitational field strength is also 11.2, which you could call newtons per kilogram or meter per second squared, doesn't matter. That just cleans up our givens a little bit. So when you come over here and you're running G is Fg over M, do a quick rearrange, and you will end up over here with what we saw before. Fg is Mg, so Fg is 2,000. You could write 2 times 10 to the third, doesn't matter. Times 11.2, and you'll get your answer. Last one. Gravitational, given units, the gravitational field strength on the moon is 1.62 newtons per kilogram. 1.62 newtons per kilogram. Now, if you recall what we said up top, noting that it's on the moon might be a good idea. Put a little M there for moon. If a spaceship has a weight, Fg, of 10 to the 6 newtons on the moon, that's important that it's also on the moon. We'll put a little M there for moon. What would be its mass on Earth? So the mass we're trying to find is not actually on the moon. We're trying to find the mass on Earth. Well, some of you may realize something about mass straight away, and if you do, good for you. I'll mention it in a minute. If not, let's come over here. We don't have much in the way of options. We got G, F, G, M. I mean, who are we going to call? I mean, I guess let me check the phone. Let me check the contacts. Nah. Oh, we could call Big Ugly. Nah. I know who I want to call. Who should we call? You guys know who to call. You want to call? We should call her. Should we call her? Let's go. Hey, yo, Shawty! Come on through. Shawty coming through. Shawty. Now, it's worth your while to recognize a huge theme in this course and in all of life. If you forget physics, I'm okay with it. But don't forget this. Coordinate your givens. If this little g is on the moon and this fg is on the moon, then this mass should too be on the moon. Coordinate your givens. Now we're trying to find mass. We do a rearrange. M equals fg over g. And when we substitute solve, m equals 10 to the 6 over 1.62. And you will get that 6.2 times 10 to the 5th kilogram. Noting that this gives you mass on the moon. Now, what some of you may have noticed in the beginning, and what you certainly need to notice at this point, is that we're not asking for the mass on the moon, we're asking for the mass on Earth. The mass on Earth is, by definition in this course, the same as the mass on the moon. So it too is 6.2 times 10 to the 5th. You could have actually written that over here in the beginning. You could have written this is the same as the mass on the moon. You'd be good to go. Just recognize that mass stays the same, location independent. The only last thing to say here is, actually, we are at the end of quarter 2. So if you want to, if you scroll back, let's see, not page 20, but on page 19, there's a nice little extra credit down here. If you're artsy about it, you're going to get yourself a little more. And then if we go back to page 18, there's 3 extra credits on here. So, anybody trying to get a little extra right before the end, feel free. Submit it in the bonus section. Do not submit it on Wednesday hoping it'll go in quarter 2. Cut that out. All right, then. Shawty!